Corona Chemistry, where we are now covering the second half of our bonding unit, which will include VSEPR, aka molecular geometry, aka shapes of the molecules, along with intermolecular forces and a couple of other minor topics such as hybridization and sigma and pi bonds. If you're brand new to this channel and you don't have too much background in chemistry, make sure you watch part 1 of this unit because you're going to get kind of lost. We covered how to draw Lewis structures in the previous video, and you absolutely have to have experience and background knowledge of what the heck we are doing. If you can't draw Lewis structures, you can't do these next few steps here. So here we go. We're jumping right into it, trying to do it in one fell swoop. The next part of Lewis structures, and once again, you do need to be able to be comfortable drawing these molecules, is we want people to assess what they actually look like in three-dimensional space. Drawing them on paper is all fine and dandy, but that's not what they actually look like. And so we pronounce it VSEPR, but it's actually written out, it's VSEPR, which stands for valence shell electron pair repulsion. Breaking down those words, essentially when we're drawing our Lewis structures here, the electrons are all negatively charged. The electrons are all negatively charged, which means they do not want to be next to each other. Therefore, the shapes that these molecules are going to occupy are a result of the electrons getting as far apart from each other as possible. And the way that we can predict their shapes is by counting this little word called domains. And a domain is either a bonded atom or a lone pair of electrons on the central atom. Keep in mind, a lone pair are electrons not involved in bonds. And it doesn't say bonds, it says bonded atoms, which is very, very, very picky there. And a lot of kids make a mistake there. But we'll highlight some common misconceptions here in a little bit. But what we're going to do is we're going to look at our chart. In the next couple of slides, include that chart, but I'm also putting a link for this chart down below the channel. I'm also putting a link to the first half of this unit's video down below as well. So make sure that if you're already feeling a little lost, that you don't know what Lewis structures are, then tune into that video first off and foremost. But here's our VSEPR theory chart. I like this one. There's a lot of them on the internet, but this one I feel like has the most information. And so we can see that on the far left-hand side, it's counting our domains, right? And then all it's going to do is once we draw the Lewis structure, all we simply have to do is count up how many bonded atoms there are to the central atom and how many lone pairs are on the central atom, and that's going to tell us the shape. That's all you have to do. Just be able to draw the structure and assess the information that you have gathered, and then you're going to be able to predict the shape. But we only go up to 6 domains, and so there is a backside to this chart right here, which is the next slide in the notes. And so we're going to go up to 6 domains. We've got multiple shapes to look at, and there's lots of kits on the internet that are really great for this. I'm also going to put a link for PhET simulations down below, which I think is the best that the internet has to offer for free as far as I've seen, if you don't have a model at home. I'm going to be holding up a few models in front of the camera. It looks like the little balls we have at the end are black, but they are in fact green. It's just the green screen that's canceling them out. But I know it's kind of hard to see, so we're only going to do minor references with those. Anyways, once again, a domain is either a bonded atom or a lone pair. Okay, keep that in mind. So now let's draw these 3 molecules, and we're going to be drawing a lot of molecules in this second half of the unit. So if you want to not have the answers spoiled for you, feel free to pause the video, draw them to your best, with your best attempt, and then you can proceed with the video to see if you did it correctly. We don't want to spoil the answers for you right away. So feel free to pause right now as we draw CH4, NH3, and H2O. And then the question is, what do these 3 examples have in common? So on the next slide, we have our final drawing of these molecules. Here's our CH4, here's our NH3, and here's our H2O. Now let's see what they have in common. Right? They all have atoms attached to the central atom, of course, and a couple of them have lone pairs on the central atom. Notice that this oxygen has 2 lone pairs that are not involved in bonds, and the nitrogen has 1 lone pair that's not involved in bonds. But let's go back to this definition of domains. A domain is either a bonded atom or a lone pair. Okay? So let's count up how many domains this central atom carbon has in CH4. Well, it has 1, 2, 3, 4 bonded atoms, therefore 4 domains. And if we look at NH3, it has 1, 2, 3 bonded atoms and 1 lone pair. Therefore, it has 4 domains. And if we look at water, H2O, it has 1, 2 bonded atoms, but it also has 1, 2 lone pairs on the central atom. Therefore, this one also has 4 domains. So they all have the same amount of domains, and yet different combinations of bonded atoms versus lone pairs, and are therefore going to result in different shapes. So let's go back to our chart and let's assess what we're looking at. Remember, we counted all three of these molecules had 4 domains, which means we're going to look at 4 domains on our chart and we're going to match it up. And let's go back to our first example. CH4 has 4 atoms attached and 0 lone pairs. So if we go to our chart here, 4 atoms attached, 0 lone pairs, that is going to result in a tetrahedral shape, as we can see here. And now let's go back to our slide here. NH3 has 3 atoms attached and 1 lone pair on the central atom. So we go to our chart and we simply, using the information that we've drawn, as long as we are accurately drawing these Lewis structures, we are going to get the correct shape here. 3 atoms attached, 1 lone pair results in a trigonal pyramid shape, right? So what's occurring here is this lone pair on top of the central atom, and I'm saying on top because that's how we've drawn it here on this page, but 3-dimensionally it can be anywhere. But what's happening is this lone pair of electrons are forcing the other atoms in a downward position. Remember, the shapes that we are seeing are a result of the electrons getting as far apart from each other as possible. And so this lone pair on the top of the central atom, I like to think of it as forcing these 3 hydrogen atoms in the downward position, sort of like a tripod, and the nitrogen is at the peak of that tripod. So what chemists named it, they named it a pyramid. And so this lone pair is really the main cause for this different shape when we compare it to CH4. And then we got H2O, who has 2 atoms attached and 2 lone pairs, still 4 domains, but 2 atoms attached and 2 lone pairs, we get a bent shape. Okay? And so I'm going to reference this by showing you one of our molecules up here in our little kit here. And so what I've got is a central atom. And originally this central molecule has 4 spots for you to attach these bonds to it, right? But we've removed 2 of them, and that's to represent the 2 different lone pairs that are sort of up here. And what's occurring is these electrons are forcing these bonds downward. They're repelling them. They're all negatively charged, therefore forcing them downward. And we get what is known as a bent position. That's why I didn't understand what all the hullabaloo is about when The Shape of Water came out a few years ago. And it got all these Academy Awards. The Shape of Water? I could spoil the whole plot for the movie for you. The Shape of Water is bent. I don't get what all the excitement is about. How boring is that? I don't even bother watching it. Ridiculous. I don't get the marketing Hollywood does. Either way, let's highlight a common mistake that kids may make. So what if we were asked to draw carbon dioxide and then assess its shape? And keep in mind, whenever we're looking at the VSEPR shapes of these molecules, we're always looking from the reference point of the central atom. You can assign a different VSEPR shape looking at each of the other atoms, but we're going to primarily look at the central atoms here. So we're looking at CO2, and this is our drawing for CO2. Carbon, of course, is our central atom. How many domains does he have? Well, the definition of domain is either a bonded atom or a lone pair. And a lot of kids make the mistake of thinking that each of these bonds is a domain. But a domain is a bonded atom or a lone pair, not a bond itself. So this carbon has no lone pairs, no dots present on the drawing, but it does have 2 atoms attached. Therefore, it only has 2 domains. And so you can see where you could have gone wrong if you're looking back at your chart. If you counted each bond as a separate domain, well, then your 4 domains would have thrown you off and given you a different shape. But we only have 2 domains, 2 bonded atoms, 0 lone pairs. So CO2, carbon dioxide, is actually a linear shape, just a straight line molecule. And so that's really all there is to it. And the shapes do get a little more complicated as you add more domains, and the different lone pairs are forcing them into different shapes, right? But aside from that, it's simply combining your drawing with the information that you have accurately portrayed in your drawing, and then comparing it to the values that you're seeing on this VSEPR chart. Okay? When we were in school physically, we were having you memorize this chart, but now that you're stuck at home in this beautiful thing known as quarantine, well, we're not watching over your shoulder to see if you're looking at this chart the whole time. So there's not too much to it with where we're currently at. So we've assigned shapes to all 3 of these molecules and even the bonus CO2. But now the next question is, how do we determine if these molecules are polar? We determined bond polarity in the last video, and that had to do with electronegativity. But molecular polarity is a slightly different concept and is so important for our last concept of today, which is intermolecular forces, right? How these molecules are actually interacting with each other. Well, molecular polarity has a little less to do with electronegativity and more to do with the symmetry of your atom. Okay, it's symmetry of, sorry, not symmetry of your atom, symmetry of your molecule. Symmetry of your molecule. Essentially, if you were to draw a line straight down the middle of your molecule, would you see the same thing on your left as you do on the right? Would you see the same thing on the top as you do on the bottom? If you do, it's most likely going to be a non-polar molecule. If you don't, well then it's most likely going to be a polar molecule. And I'm not a very visual person. And so when I was in high school, I struggled with this. Okay, but you have to think of these molecules three-dimensionally, and that's why having one of these little model sets is very helpful. And so feel free to consult that virtual PhET site down below. But you have to be able to think of these three-dimensionally. Okay, so looking at this right away, NH3, and it's not showing that lone pair of electrons we have on the top right here, but those electrons are there. They didn't show it in this picture, and it's a polar molecule. Why is it polar? Well, keep in mind that those lone pairs are forcing those atoms downward, which means they're all tilting downward. And so if I drew a straight line down the middle, I'm not seeing the same thing as I do on the top as I do on the bottom, because everything's being tilted downward. Here's a really great rule of thumb. And this is not a cut and dry rule. It's not a law of nature. But if the central atom has a lone pair or more, then it is most likely polar. Very good rule of thumb to follow. The only exceptions to this are square planar shapes, okay? Square planar shapes and linear shape here. Not linear with two atoms attached, but actually the linear shape that is occupied with 5 domains, 2 atoms attached and 3 lone pairs. Another way you can make any molecule polar if you swap out one of the atoms. Keep in mind, we've got CCl4 right here, carbon tetrachloride here in the middle, and then we've got CH3Cl, 3 hydrogens attached and 1 chlorine. Well, when we look at the individual bonds, we can determine if they are nonpolar or polar or ionic using their electronegativity. But if they're all the same bond, then they're all pulling the same direction, so I don't have to worry about that there. And so in each of these bonds, chlorine is more electronegative than carbon, and so therefore it's winning the tug-of-war battle. But down here, carbon and hydrogen are very similar in electronegativity, so they have a very small difference there. But carbon and chlorine, carbon is definitely losing this tug-of-war battle, and so this chlorine is pulling in a different direction and a different way than these other hydrogens. Therefore, it's a totally different perspective looking from that chlorine. And so if I were to draw a line down the middle here, just following my cursor here, well, I would get 2 hydrogens on the left and 1 hydrogen and 1 chlorine on the right. And that's, of course, not symmetrical. Therefore, we can make any molecule polar if we simply swap out one of those peripheral atoms. So that's a really good rule of thumb. But as far as you're concerned in this course, pre-AP, on-level, general chemistry, whatever you're doing here, if your central atom has a lone pair, it's more than likely going to be a polar molecule. Okay? So that's all there is to that. And there are some shapes that are always polar that simply can't help it. And so this is going to go in line with our, does it have a lone pair or not? Well, trigonal planar, we have an example of that right here. And notice it sort of looks like they're pulling in different directions. But if we're looking at our chart, in the VSEPR chart, they all go to the same angle, which means it sort of forms an equilateral triangle here, which means all of their pulls are canceling each other out. Trigonal planar is always a nonpolar molecule as long as all the atoms attached are the same atom. Linear, same story. As long as the atoms attached are the same atom, like in the case of CO2, then it's going to be a nonpolar molecule. Trigonal pyramidal. This molecule, this shape of molecule, has a lone pair on its central atom. Therefore, no matter what the atoms are that are attached to the central atom, this molecule will always be polar. Tetrahedral. No lone pairs. As long as every atom attached is the same, it's a nonpolar molecule. Same story for trigonal bipyramidal. There's no lone pairs, so therefore, as long as every atom attached is the same, and what I mean by the same is, are they all hydrogens? Are they all chlorines? Not a mixture of chlorines and hydrogens. Seesaw. it has lone pairs on it. Therefore, it's going to be polar. And it can't not be polar. It will always, always, always be polar. Same for T-shape, right? I know a lot of you playing your video games know very astutely what the T-shape is, right? In the bad manners world. Like so. My arms are out stretching wide and they're canceling each other out. However, the third leg to the T is going straight downward and there's nothing there to cancel it out. It has lone pairs on the central atom, therefore it is always going to be polar. Octahedral, as long as all the atoms are attached, it is going to be a nonpolar molecule. How do I know that? It has 6 atoms attached and no lone pairs. No lone pairs on the molecule, and as long as they are all the same atom, therefore means it is a nonpolar molecule.
Quarantine log. Day 59. The old saying goes that the clothes make the man. If that's the case, I really hope I picked the right clothes because I've worn the same ones for the last 26 days.
Before we dive into intermolecular forces, we're going to cover a couple of minor concepts as far as our class and our curriculum is concerned. We're going to talk about hybridization of orbitals from the perspective of the central atom, and we're also going to talk about sigma versus pi bonds. So hybridization is a rather complex visual, and is sort of a more complicated concept in explaining what is actually going on. If you can imagine a bond, right, which we represent with a straight line between two atoms, well, a bond is not literally a straight line or a rope tied or a string tied between two atoms. In the real world, it's actually just the overlapping of electron clouds. And then the electrons are free to roam in the cloud that they are overlapping with. And so the electrons are just roaming back and forth between the partners involved in the bond. And what this does, seeing as in the last set of videos concerning electron configuration, we now know the shapes of these pathways, or what we know as orbitals, we know that there's different shapes to it. We've got S sublevels, P sublevels, D sublevels, F sublevels, and they all have different shapes, right? Well, different combinations results in different hybridization of orbitals. But it's actually very, very simple math here. Because in our VSEPR chart, we only go as high as 6 domains, right? Our hybridization is only going to add up to 6. So notice, if I've got 2 domains on the central atom, well, remember, we're not going to fill up the next sublevel until the one before is filled. It's one of those rules of thumb that we learned in the electron configuration unit. So the first sublevel filled is always the S. But a little bit of review, how many orbitals are in S sublevel? Well, there's only one. And so I can't move on to the P until this S sublevel is filled. But for 2 domains, if the first one is in the S, then I only need one more, and so I'm only going to need one in the P. But with 3 domains, the first one filled will be S, and then the next 2 will be P. For 4 domains, the first one will be S, and the next 3 will be P. However, the P sublevel only has 3 orbitals, and once they are all used up, it's filled. No more space available for more electrons to overlap and hybridize. And so we're going to have to move on to the D sublevel. But keep in mind, we're only going up to 6 domains here, so we're only going to get slightly more complicated. And as it stands with hybridization, if you're looking at more complex molecules, okay, which this typically happens the further you get into chemistry, maybe you're studying AP chemistry, maybe you're in college looking at general chemistry or organic chemistry, these molecules get a little more complicated. You can talk about the hybridization of each of these atoms. Typically, in our course that we're talking about, we're sticking to molecules that look like this, and so the hybridization that we're concerned with is simply the central atoms that you're looking at, the carbon, the oxygen, the nitrogen. But if you can count the domains, well, then the number of domains, notice that all of these superscripts, and keep in mind it's not written here, but there's a 1 and a 1 here. 1 plus 1 is 2. 1 plus 2 is 3. And then let's go down to 6. 1 plus 3 plus 2 equals 6. If you can add up the superscripts, they must add up to the number of domains on the atom that you're analyzing for hybridization. That is the most simple way of explaining this. Right? If you've got chemistry background or you are a chemistry teacher yourself and you're watching this video, you might be cringing at this explanation. It is the most simple mathematical way of explaining it. It's not giving you a direct visual of what is actually going on, right, when these electron clouds overlap, but it gets you the information that you need because all the questions that they're asking are simply what is the hybridization of a specific atom in a molecule. And so that's going to get you what you need. Count the domains and the superscripts must add up to the number of domains, okay? Or you can simply look at this list right here, and if you know how to count domains, well then, congratulations, that's the hybridization of the atom that you're looking at. So honestly, no brain power required. Don't need the 200 IQ, if you know what I'm saying. Next, we're going to learn how to count sigma and pi bonds, okay? The sigma bond is the first bond formed between any two atoms. So these two atoms are getting together. They know they're going to get into a relationship with one another. They don't know if it's going to be a single, a double, or a triple bond, but they know they're going to get together in some way, shape, or form. And so they're going to initially form that first bond. And it's the strongest. The sigma bond is much stronger than a pi bond. Every single bond is a sigma bond. But then after that, as they're talking it over and they realize in this relationship, some of us, we might need more electrons than we initially let on. Okay, a little bit of deception up front. And so they realize they're going to have to invest more electrons into this relationship. So that's why the double bonds and the triple bonds exist. Well, after the sigma bond, every bond formed between two atoms is what is known as a pi bond. And it's a little bit more of a reach for these electrons. If you're drawing out using the Lewis dot structures, you can see that the two electrons on the innermost section, in the middle section of your atoms, are really, really close to each other. And if you're connecting the electrons up top or down below, it's a little bit further for them. And so these pi bonds are stretching a little bit further, and therefore they're a little bit weaker. So let's make this very, very simple. Every single bond is a sigma bond. Every double bond contains a sigma bond and a pi bond. And every triple bond contains a sigma bond and two pi bonds. Why is that? Because the first bond formed between any two atoms is always a sigma, aka why there's one sigma in each of these, but everything after that is a pi bond. And so when I'm looking at this bottom right image, are there any pi bonds present? Pause for effect. No, there are no pi bonds because there are no double or triple bonds. They're all single bonds, which means they're all sigma bonds. And so all you have to do is count these lines. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 sigma bonds, right? I hope that's not a mistake. If I counted wrong, that's so hugely embarrassing on YouTube. And the internet is a critical beast. So please, spare me. But now we look over here at this molecule in the bottom left. Now I'm seeing some double and triple bonds, but how many pi bonds are there? Well, the first bond formed between any two atoms is a sigma bond. Every double bond contains one pi bond, and every triple bond contains two pi bonds. So I see one double, so that's one pi, and I see one triple, so that's two more pi. So that's a total of 3 pi bonds. Now, how many sigma bonds are there? Well, there's a sigma in between any two atoms in this molecule. So anytime you see a connection between two atoms, you have to count it as a sigma because the first bond formed is always a sigma. So 1, 2, 3, 4, 5, 6 sigma. 6 sigma, 3 pi. All right? And we can get really, really spicy with this. And we can count the sigma and pi bonds in much more complicated molecules such as cocaine. But we can save that for another video. It gets a little more complicated because how organic chemists actually draw their molecules is they get kind of lazy because there's a lot of atoms involved. And at each one of these hard edges, these points on these seemingly geometric shapes, is actually a carbon. And every carbon has to have a full octet, so sometimes they get lazy and they don't even draw all the hydrogens that are bonded to the carbons. And so that, as I said, much spicier than counting the sigma and pi bonds here. But seeing as we're just studying the very basics of general chemistry, if we are asked to draw a molecule like CO2, as we were done earlier, how many sigma bonds are here, how many pi bonds are here, that's all you're going to really need here. So 1, 2 sigma bonds, because any bond between any two atoms is always first joined with a sigma bond, and anything after is a pi bond. In a double bond, there's 1 pi. In this double bond, there's 1 pi. So 2 sigma, 2 pi in CO2. And that is sigma and pi bonds.
Quarantine log. Day 62. We've had to adapt. With the scarcity of certain paper products in the world, I've resorted to noting my dog's behavior. I've begun to drag myself across our rug. It's working. Not a rash yet.
So the last topic of today's video is intramolecular forces and intermolecular forces. Our discussion thus far has always been, in this entire unit has been concerning the intramolecular forces. Intra means within. And so it's talking about those individual bonds that occur between these two atoms. Ionic bonds, polar bonds, nonpolar bonds. And they are much, much, much stronger than intermolecular forces, which is what we're going to talk about now. Intermolecular forces. Inter means between, right? When I have a cup of water, I don't just have one molecule of water in there. I got billions and billions of molecules of water in there. Well, how are they behaving? How are they interacting with each other? And those are the intermolecular forces that we are talking about. But they are significantly weaker than the intramolecular forces. A lot of people get it confused. Whenever you're boiling a pot of water for a nice bowl of spaghetti that you're making for your lovely lady that you're having over this evening, right? A lot of people think that when you're boiling water, you're splitting water molecules, that you are dividing hydrogens from oxygens, and then you're getting hydrogen gas and oxygen gas in the air. Well, that's just not at all what's happening. Because then you'd have flammable hydrogen gas and oh so sweet oxygen that you're breathing in on the other side, and it's just not how it works. But what you are doing is you are breaking the intermolecular forces between the water molecules. Yes, I'm separating H2O from H2O, but I am not separating hydrogen from oxygen. And the reason why I can't do that is because the intramolecular forces are so much stronger. So with intermolecular forces, there are three that we're going to talk about today, and we're going to go in order from weakest to strongest. And when I say that, that means in general. Yes, there are some exceptions in which the weakest forces are stronger than the next step, but it's certain circumstances, and we'll talk about that. The first on our list are what are known as London dispersion forces, or some teachers interchangeably use the term van der Waals forces, but we're going to stick with London dispersion forces. You might see us abbreviate LDF on sheets or quizzes or tests. You might see that online places. But the London dispersion forces, let's read this definition. All covalent molecules and atoms possess and exhibit these forces. The attractive force is created from the constant motion of electrons creating instantaneous dipoles, meaning for just a split second, these atoms or these molecules that you're looking at are polar for just a brief second. What the heck does that mean? Well, let's get a little visual here. Moving on to the full screen. I will give credit to this YouTube video down below. I love it for this. Colombian coffee, the richest coffee you could ever get. Pay attention.
I love you.
Champagne is now being served on the after deck.
By the way, when will your inheritance come through?
Lobster is now being served on the promenade
I
deck.
love your villa at Monte Carlo.
Colombian coffee is now being served in the starboard side lounge. No wonder so many people's preferences lean toward 100% Colombian coffee. It's the richest coffee in the world. Handpicked by Juan Valdez.
Juan Valdez, the richest coffee in the world. You heard it here, folks. Now, the lady in this video, she ain't nothing but a gold digger. But that's not what we're focusing on, okay? We're focusing on when all the patrons of the cruise went to one side, what happened to the boat? Lean with it, rock with it, lean with it, rock with it. The boat tipped. Well, imagine every person on that boat is an electron. Now, yes, these electrons are all negatively charged, and they want to stay as far apart from each other as possible. But through their random motion, what if for just a split second, an instantaneous moment, more electrons were on one side than another? Well, if more electrons are on one side than another, like we see in this left circle here, this left atom, more electrons are on the left and the right, well, this side is more negative than this side, which is more positive. An instantaneous dipole. And what we're looking at here is this is simply individual atoms. So for just a split second, this atom is negative on the left and positive on the right. Well, let's just say that a neighboring atom is experiencing the exact same scenario. More electrons on the left than on the right. Well, what's going on right here? A little bit of chemistry. A little bit of positive, negative, a little bit of Paula Abdul opposites attract action. 2 steps forward, 2 steps back. We come together because opposites attract. If you haven't heard that song, please go to your Spotify, your Apple Music, or YouTube, whatever you're listening to, and add it to your playlist immediately and culture yourselves, ladies and gentlemen. Paula Abdul theory of chemistry states that opposites attract. So for just a moment, these atoms want to get next to each other. Okay? For just a moment, they want to get next to each other. But then in the next moment, the electrons spread out again, and then there's no attraction. It's like the constant up and down, whether you like someone in your class or you hate them, you like someone, you hate them, you like someone, you hate them. It's just the constant up and downs of the romance in high school. Focus on yourself, kids. Okay, focus on yourself. Better yourselves in education, then focus on the boys and the girls. Okay, all right. Love comes after yourself, because to love someone, you first have to love yourself. Anyways, London dispersion forces are exhibited by every single atom, every single molecule that's got electrons. Okay, so everyone exhibits it, which in turn is kind of why it's the weakest. Everyone's got it, so therefore it's nothing special. Everyone's got it. And this is the only intermolecular force that non-polar molecules exhibit. Very, very important. This is the only intermolecular force that non-polar molecules exhibit. So let's move on to our second. Okay? Dipole-dipole, which traditionally is stronger than the London dispersion forces. Sometimes you'll see this abbreviated dip-dip on pages or assignments, right? But what this is this is the attractive force between polar molecules. And what I mean by traditionally stronger than London dispersion forces, there are some times where LDFs are stronger than dip-dips. And the reason why is the more electrons you've got, well, the stronger your instantaneous dipole is. And so the further you go down on the periodic table, the more electrons you've got, therefore the bigger your instantaneous dipoles are, right? So, of course, there will be circumstances where something with only London dispersion could be a stronger intermolecular force than something with dip-dip. But it's all circumstantial. You have to look at each situation, okay? So now let's talk about dip-dip. And the reason why dip-dip is typically stronger than LDFs is because these were fleeting feelings. This attraction that was exhibited between these two atoms was only for a moment. And then in the next moment, they didn't feel anything for each other. But when it comes to a polar molecule, these guys always have the positive and the negative. It never disappears. Therefore, the attraction between the opposites is always there. Therefore, there's no, I love you, I hate you, I love you, I hate you. It's always, I'm attracted to the opposite. It's always positives attracting negatives, negatives attracting positives. Okay? And so it's not fleeting. And so anytime you have a polar molecule, you are experiencing that the molecule is exhibiting dip-dip, otherwise known as dipole-dipole forces. The last intermolecular force that we're going to talk about is hydrogen bonding. And although the name indicates that it's anything attached to hydrogen, it's very, very special. It's hydrogen bonded to an extremely electronegative element. Okay? And these three electronegative elements that we're talking about are fluorine, oxygen, and nitrogen. Okay? The way that I was told, remember this in high school, is chemistry is so much gosh darn fun. F-O-N. It's a lot of fun as well, too, if you're doing it right. But fun just hits different, right? And so it's an extra strong version of a dipole-dipole bond. It is a dipole-dipole bond. It's just extra strong because there's such a large difference in electronegativity between the fluorine, oxygen, nitrogen, and the hydrogen that it's attached to. So just because something's attached to hydrogen does not mean it's exhibiting hydrogen bonding. It has to be attached to one of these three elements, like we see in water. Oh, now we're seeing why water is so unique and why we learned it's so strong and the surface tension and all the different properties of water that are super unique. It's because of the intermolecular forces between these molecules. So now, to finish up today, we're going to look at a couple of questions which are going to require us to draw Lewis structures. If you can't draw Lewis structures, you're not going to be able to do intermolecular forces and assess these questions here. Determine what intermolecular forces each molecule exhibits. This is going to be one of those moments where if you'd like to try your best on drawing these molecules, feel free to pause this video now so that the answers are not spoiled for you. Because in the next slide, you will see all of the molecules drawn out for you. If you want to practice, go for it. Pause for effect. And here we go. We have our drawings of all of our molecules here, our Lewis dot structures, and we are going to assess what intermolecular forces each of these molecules exhibit. We're not only going to list the strongest, we're going to list each of them. Okay, so starting with CO2 up in the top left, notice that there's no lone pair on the central atom. and each of the atoms attached to the central atom are the same, which means this is a nonpolar molecule. And if you are a nonpolar molecule, then what is the only intermolecular force that you could possibly exhibit? Well, it's the force that everyone exhibits, which means carbon dioxide only exhibits London dispersion forces, LDFs. Okay? Does not exhibit dip-dip because it's not a polar molecule, and there's not even hydrogens here for it to even, have a chance at exhibiting hydrogen bonding. So this one only has London dispersion forces. It's a completely symmetrical molecule, therefore it's nonpolar. Now we're looking at NH3. We've looked at him a couple of times this video. NH3, we've got 3 atoms attached, right? 1 lone pair, and this lone pair on the central atom means it's going to be polar, but every molecule always exhibits LDFs. So this guy absolutely exhibits LDFs, and everyone on this page exhibits LDFs, okay? But we're going to list all of them that they exhibit. Because this lone pair is here on the central atom, it is a polar molecule. This is a trigonal pyramidal shape if you're looking at your VSEPR chart, which means it's forcing those hydrogen atoms in the downward position, which means it's not symmetrical. If I were to draw a line through the middle, I would not see the same thing on the top as I do on the bottom. It's not symmetrical. So, because it's polar, it exhibits dipole-dipole forces. But does it have our third and final intermolecular force? What is this? A hydrogen? But just because it's a hydrogen doesn't mean it exhibits hydrogen bonding. However, chemistry is so much gosh darn fun. Hydrogen is attached to one of our magical elements, nitrogen, which means NH3 does exhibit hydrogen bonding as well. So this molecule exhibits all 3 types of intermolecular forces. Just so happens that the hydrogen bonding is the strongest intermolecular force that it exhibits. So now let's look at CH3Cl. Okay? Certainly not symmetrical. If you were to draw a line, you would not see the same thing on the bottom as you do on the top, the left on the right. You simply wouldn't. This chlorine being here throws a little curveball into the mix. Of course, it exhibits LDFs. Everything exhibits LDFs. But because it's not symmetrical, it is also a polar molecule. So therefore, it's going to exhibit dipole-dipole forces. Does it exhibit hydrogen bonding? I see hydrogens! However, it's not attached to one of my FON elements. It's not attached to oxygen, fluorine, or nitrogen. Therefore, this molecule only exhibits LDFs and dipole-dipole forces. Going to sulfur hexafluoride, the gas that makes your voice sound like Darth Vader. Completely symmetrical, right? If you draw a line any which way, you're going to see the same thing on each side. So it's a nonpolar molecule, which means the only intermolecular force that it's ever going to exhibit are those London dispersion forces. However, this guy's got a lot of electrons to work with. Therefore, he's probably got some pretty big LDFs to work with. Either way, that's all he's got. He's not polar, therefore it's only LDFs. Hydrofluoric acid, HF. If it's a bond between 2 different atoms, and those are the only 2 in the molecule, well then, of course, it's a polar molecule, right? Because if I draw a line, I'm not seeing the same thing on the left as I do on the right. Of course, it exhibits LDFs. Everyone exhibits LDFs. It is a polar molecule, so it does exhibit dipole-dipole or dip-dip. Does it exhibit hydrogen bonding? Well, hydrogen is directly attached to fluorine, one of my 3 FON elements. Therefore, this one does exhibit all 3. Now we're looking at hydrosulfuric acid, H2S, and I even put in a picture that doesn't 3-dimensionally show what it really looks like accurately. This is just, how you would draw it on the page, but this is not how it looks 3-dimensionally. So we have hydrogens attached to sulfur and 2 lone pairs on the central atom, and because it has those lone pairs, that's pretty much telling you right away that it is a polar molecule. Because 3-dimensionally what's occurring is those electrons are forcing those hydrogens in the downward position. So this actually has a bent shape just like H2O, just like water. So it is polar. Of course it exhibits LDFs. It is polar though, so therefore it exhibits dip-dip. And I see hydrogens. Does it exhibit hydrogen bonding? No. Because it is not attached to one of my FON elements. Therefore, this simply exhibits LDFs and dip-dip. So, this question asks for us to list every IMF that a molecule is exhibiting. A lot of the time, they'll simply ask you to identify what the strongest intermolecular force that a molecule is exhibiting. So, just go in order. If it only exhibits LDFs, then of course that's your answer. If it exhibits LDFs and dip-dips, then dip-dip is your answer. And if it exhibits all three, then hydrogen bonding is your answer. So our third and final question is having us utilize all of our knowledge. We have to be able to draw, we have to be able to assign IMFs, and we have to be able to analyze which are potentially stronger. Rank the following from lowest boiling point to highest. Okay, so we've got 5 molecules here of varying shape and size and intermolecular force. We've drawn them all out, which is your first step anytime you're attacking this. Well, here's the deal. When you are boiling something, what you are doing is you are disrupting the intermolecular forces. So the stronger the intermolecular forces are, the more heat energy you're going to have to put in order to boil it. So stronger IMFs means higher boiling point. And so what we need to be able to do is assess what IMFs each of these molecules are exhibiting. And notice I tried to stagger them so they wouldn't overlap with each other, but hopefully you can easily track which is which. So let's start with CH4, which we've drawn out. Completely symmetrical. If I draw a line down the middle, I'm going to see the same thing on the left as I do on the right. So he's only going to exhibit LDF. He's a nonpolar molecule. He only has London dispersion forces. Same with this carbon chain. He's a little more complex, but any way you slice it, it's completely symmetrical. Okay? So he's only going to exhibit LDFs. Okay? So we've got 2 molecules that each only exhibit LDFs. So we'll come back and we'll talk about that. Now let's go down to water. We just talked about water a few moments ago. Water is the staple poster boy example of hydrogen bonding, right? It's hydrogen directly attached to oxygen. It's a polar molecule. It's got LDFs. It's got dip-dip. And it's got 2 separate hydrogen bonds in it. So very, very, very good there. Now we're going to look at an alcohol here, which as we can see here, it is not symmetrical. If we draw a line, we've still got that random oxygen and hydrogen hanging off to the side that we don't see on the other side. So it is certainly polar, but it also is exhibiting hydrogen bonding because we've got a hydrogen attached to this oxygen right here. All of these over here are not hydrogen bonds. It's only this one over here. Very, very important. Next, we look at pH3. And pH3, when we draw it out, has a trigonal pyramidal shape. It has 3 atoms attached in 1 lone pair. This lone pair means that it's polar. So it doesn't only have LDFs, it also has dip-dips. But does it have hydrogen bonding? No, because it's not attached to one of our 3 highly electronegative elements, fluorine, oxygen, or nitrogen. So this guy only has dip-dip. So taking that all into consideration, we sort of have different tiers for these guys where we're going to place them. These 2 are definitely in last place. We don't know the order yet. They're definitely in last place, though, because they only have LDFs. And then pH3 is right in the middle. He's going to be 3rd place because he's got dip-dip, but he doesn't have hydrogen bonding. And then we got to figure out what to do with these final 2. Okay? Who's going to come in 1st place? Who's going to be in last place? So let's talk about CH4 versus our chain right here, our carbon chain. Well, in a lot of cases, okay, we're told that size does not matter. In chemistry, it begs to differ. In chemistry, the bigger you are, the bigger your LDFs are because there's more electrons involved. There's a whole lot more of electrons involved in this chain than there are here. More electrons means more LDFs, stronger LDFs, greater instantaneous dipoles, which means C3H8 has stronger intermolecular forces than CH4. So this guy, CH4, is in last place. He's our lowest boiling point. And C3H8 is going to be a little bit higher than him. We don't know how much higher. We don't care. We're not going to mathematically calculate it. We simply want to rank them. Okay? So CH4, last place. C3H8, 4th place. pH3, 3rd place. All that's left is right here. And you might use the same logic here. Oh, this guy is a whole lot bigger than this guy. Size matters! But actually, size matters when it's only a tie. This is not a tie. Kind of misleading here. Because more hydrogen bonds means stronger IMFs every single time. This guy only has 1 hydrogen bond. This alcohol only has 1 hydrogen bond. Meanwhile, in every single water molecule, there are 2 hydrogen bonds, which means water is going to have the highest boiling point out of all of these. So let's go back and rank them. 5, 4, 3, 2, 1. And that is the solution to our final problem in our notes. Once again, feel free to use the notes and slides. We should have mentioned this at the beginning of the video, but Links to those are located directly beneath this. Feel free to subscribe to this channel if you're not one of my own students who are using this video, as we're going to be posting as long as we're in quarantine. Aside from that, good luck in bonding. Chemistry is great, even from home.